Hello dear colleagues, I'd like you to present our work Modeling of Neural Systems and Networks by Functional Differential Equations. The work considers models of neural systems in the form of functional differential equations, models with distributed delay obtained by generalizing their corresponding systems with discrete delay described by differential-difference equations. It is shown that such a generalization allows, while preserving all the capabilities of models with discrete delay in terms of simulating self-oscillations characteristic of neural networks, to give the latter a more adequate character. This is confirmed by the results of modeling the Hutchinson system with distributed delay using Matlab tools, which showed the presence of a period and the nature of self-oscillations depending on the model parameters, and therefore the feasibility of burst and single transmission of nerve impulses. The capabilities of systems with distributed delay in the feedback circuit due the multiple propagation path of disturbances, both in the interneuron medium and in the network connections are shown. During the simulation, the distribution of delay approximated by a second-order polynomial in a system of independent exponential functions is considered. A great number of works are devoted to the mechanisms of processes running in neural networks of living organisms and their models. According to the title of the article, the purpose of this paper is not differential-difference models, but models of functional differential type, models with distributed delay, which can be obtained using an appropriate generalization of models with discrete delay. Certainly, if in the theory of equations with distributed delay there is also a lot of literature, then not much is known from its application, especially in the field of neural networks, for example, for monograph. Discrete delay neural system models. The first model suitable for this generalization, the model proposed by Hutchinson and named after him, is described in the basic ecological equations, which can be given the following form. Functional differential methods. The system obtained from the Hutchinson model with a distributed delay can be defined by the species functional differential equation. Here G from T and tau is a core of Stieltjes integral, and Y from T is an input effect. Delay distribution and relaxation after oscillations on figure 6. Figure show the auto vibration of relaxation type. First D 0.25, second D 0.5, third D 1.0, and 4 D 2.0. Distributed delay and auto oscillations. First D 2.5, second D 3.0, and third D 4.0. Figure shows the oscillations approaching the harmonic form. The dynamics of the control parameters is shown in next figure. In this case, parameter Q 0.275 and normalizing factor H 0.385. The memory depth of past values is assumed to be 20 microseconds. Other differential-difference models of neural networks presented in the first chapter are summarized in the same way. As in the case of the Hutchinson model, they may well be solved by the step method. Here we'll focus only on the delay feedback models presented in the figure. The model shows its application to the multiplicity of interneural and network perturbation paths, which determines the distributed nature of the feedback encompassing neurons. The operator f from p is usually considered to be either a rational function with an exponent of denomination less than 3, or the functional operator q from p is considered to represent the van der Pol equation. The exponent of the polynomial p from q is usually less than exponent q from p. From above equation we can see the obvious analogy of the method of its solution with the Hutchinson equation solution method. Certainly, the solution of the equation with delay feedback puts on the task of analyzing its stability, a task that is the subject of a separate study. Thank you for your attention.